Today, we embark on what I just know is, I know is one of everybody's favorite subjects. That's the sarcasm in my voice, which is fractions. Now, we're not dealing with just numbers, we're dealing with expressions. So what we're talking about is what we call rational expressions and rational functions. And we'll get to exactly what we mean by that in a minute. This is in your book, section 7.1. I've been kind of going over in my head a little the course, and I didn't set things up to assign an assignment yet, but I will do that. I'll try and do that tonight, put it on Canvas, the homework for this. So we're going to backtrack a little. We're going to talk about a rational number. A rational number is a number of the form a over b, where a and b are integers. And but b cannot be 0, because this is like division. You can't divide by 0. And the risk of seeming like we're back in grammar school, I'm going to go over how we multiply. You'll see why in a minute why I'm going over this, how you multiply and divide these numbers. Divide. So if we have a number a over b times a number c over d, I think you're all familiar with the idea that we can multiply the numerators and the denominators, and we can get our result. Not the same, but similar if we want to divide two numbers c over a over b divided by c over d, which we can write, we're careful the way we write it. The way we do this, of course, oh, you gave me the eyebrow, like, wait, what confused you there, if anything?
Oh, nothing, I'm just slow.
You're sure?
I'm just writing slow.
Oh, okay. Okay. To divide, well, instead of dividing fractions, we multiply by the
denominator.
No. We're dividing fractions.
Reciprocal.
So we multiply this thing's dead. This doesn't seem a lot better. Instead of dividing by c over d, we multiply by
D over C.
d over c, which is called the reciprocal. Okay. Good vocabulary word. All right, so that's pretty straightforward. Adding and, it's funny, usually, you think of multiplying and dividing as more complicated than adding and subtraction, but with fractions, when you're trying to add, I have to go to Dave and see if I can find a better pen. Yes, I have a better pen. I need a common denominator. So in the worst case, I can use the common denominator b times d. I mean, if b and d are the same, it's easy. If they have common factors, it can be easier. But worst case, I can always use a common denominator of bd, in which case this becomes AD and C over D becomes, let's say, CB. All right? So, like as an example, 1/5 plus 2/3, well, 5 times 3 is 15. 3 times 1 is 3, and 5 times 2 is 10. That's my CB, my AB, and I get 13 over 15. Hello. Now, I'm going to cheat a little here, because I have a blackboard. When I want to subtract, it's just a matter here of changing all these pluses to minuses, right? So this would be -7, right? It's the same basic idea. And if you think of C as, C could be, C were a negative number, and you can just leave it as positives and plug in -C. It comes out the same. Okay. So,
Professor,
yes.
isn't the part right next to the equal sign, isn't it supposed to be A times D minus C?
Yes, it is. I'm glad you noticed. Today has been a terrible day for me. My brains are not working, so everyone be on alert for mistakes. Thank you. You're paying attention, which is really the most important part. That doesn't mean I can say everything wrong and you'll get it right. But. Okay, so this is just numbers. As I said earlier, we're going to talk about rational expressions and functions. So what we mean by that, instead of just numbers a over b, we mean polynomials. This is my way of writing a polynomial, one polynomial or another, over the other. We'll give you some examples in a minute. The one restriction here is the same restriction we had over there, which is q of x cannot be equal to 0, because of course we can't divide by 0. All right. So the first thing I'm going to talk about for rational functions is the range, right? Not the range, I'm sorry, is the domain. The domain of the function, if we don't tell you what it is the most expansive domain we can have, right? Hopefully it's all real numbers. But for a rational expression, q of x cannot be 0. So for example, if I have a rational function, f of x equals 4 over x minus 2, I don't want the denominator to be 0, right? Which would occur when x is equal to 2. So if I don't tell you the domain of this function, you can tell me, well, you could write it this way, all reals except x is not equal to 2, except 2. There are other ways to write it. You could write it as negative infinity to 2 and 2 to infinity. These parentheses, I don't know if you remember what we call it an open interval, meaning we don't include the endpoints. So we're not including 2 here. Or you could say all real numbers x not equal to 2. You can, just as long as we ask for the domain, you indicate clearly that 2 is not allowed. All right. So that's the domain of a rational function. The range is a little harder to determine. The range is what possible values it could have. Now, I'm going to show you what the graph of this looks like. You can, of course, always if you're working on homework, you can always use the program I'm using, Desmos, and plug in the function. Okay, I think it's coming up here. So we have 4 over x minus 2. And let's look at this graph for a minute. We could pick out some points on here. We could say, what happened? There we go. Let's say we picked out a point 6. Well, we see the function has value 2. Sure enough, 6 minus, did I say that right? No, I didn't. 6 would be 1. Okay, so 6 minus 2 is 4. 4 over 4 is 1. So that's why we get the point 1 here. You'll notice that as we get close to 0, this kind of goes up off to infinity, but it gets closer and closer to this axis. No, it doesn't get closer and closer to this axis. It gets closer and closer to 2. Right? Here, this line, x equals 2, is called an asymptote, which I feel like I need to write because there's a silent, sort of a silent P in there. This, of course, is a vertical asymptote. As we go out here to infinity, this is getting closer and closer to this axis, to the value 0. So that's a horizontal asymptote. And I don't know if we'll run into them in this class, but it's possible to have, say, a line that's not vertical or horizontal, but you could still have a function, approach it as close as you want, never reaching it. You have a non-horizontal or vertical asymptote. All right. Okay, so I was talking about the range. The range is the y values. So we see here that as you get closer and closer, we get all the y values all the way up to infinity, and all the y values down to negative infinity. There's just one value which we never get. Does everyone see what that is? That's actually where the asymptote is.
0?
0, I heard that. Yes. We can't evaluate 4 over x minus 2 and get 0. Right. I want to hide this for a second. Yes. We'll line it this way. Here's another example. F of x equals 5x over x squared minus 16. Okay, again, we have a polynomial p of x over another polynomial q of x. And if we're interested in the domain, we need to find out where the q of x could be 0. So if x squared minus 16 is 0, this is one of our important patterns, a squared minus b squared. So we can immediately factor it. X minus 4 times x plus 4. And we can see that if x is 4 or minus 4, the denominator would be 0. And those are the only places where that will happen. So the domain is all real numbers, x not equal to 4 and x not equal to minus 4. Now, as in the other example, there was a vertical asymptote at 2. Since we have this function going to 0 at both 4 and negative 4, we might expect the same kind of behavior. Asymptotes at 4 and minus 4. We'll take a look at that in a second. We also we want to know what the range is, and I'm going to show you the graph because I think it, in this case, the picture is going to be better than all my words. So, I don't know if did I put the right, what did I put here for my example? Yes, I put the right example. Put 5x over x squared minus 16. Okay, so here we see that just as we thought at 4 and minus 4, that these asymptotes. The function comes close to minus 4, it gets closer and closer to an infinite, a big number from this direction, from the right. From the left, it goes down to negative infinity. Same thing here at 4 as at negative 4. And as we go out this way, again, there appears to be a asymptote at 0. However, in the center portion here, you see we go through this value, 0. So the range is going to cover all values of y. The range is all real numbers. So there isn't a general rule I can give you. We have to, we have to look at each function to see what happens to the range. While this is up, I just want to try a slightly different example. I'm just making this up as we go. This is going to be x to the 4th over x squared plus 2. Right? Well, before I put it up, what would we expect about the domain of this? Anyone have any thoughts on that? And where can this denominator be 0? How can I plug in an x and get 0 here? You have to think about this for a second. Is everybody thinking about it? Anybody have any ideas? Any thoughts on this matter? I know it's late in the afternoon and lunch is kind of hitting, but what happens if I plug in a positive here? A positive number. If I plug in a negative, I get a positive number. If I plug in 0, well, 0 plus 2 is still a positive number. I can't make this 0. That tells me my domain can be all real numbers, right? Okay, let's take a look at it. This one's a little different from previous. do recommend, you know, if you're doing homework and something's kind of confusing, consider, you know, playing around with this program. It can be very useful. Ah, okay. So what do I see here? My domain, I can go off in either direction and I get a value. They just get very large as I move outward. But my range, you see there are no points down here. Right? So my range is just y's where, you know, y is greater than or equal to 0. All values greater than or equal to 0 in the range of this function. Okay. So I guess I'm going to turn this off again. All right, so that's rational expressions, rational functions. There's a few tricks for dealing with these that you should know about. Let's take, for example, 2x cubed minus 6x over 6x squared. Okay, well, the first thing to notice is that if x is 0, zero can't be in the domain, because if x is 0, I'm dividing by 0. So my domain is all real numbers, x not equal to 0. But just looking at this is a little complicated. I'm not really sure what this is, but we can simplify this. All right, I can factor. Right? So I have 2x, x squared minus 3, and here, well, I can also have a 2x times 3x. Now, since 2x over 2x is 1, I don't have to look at the whole expression. I can just look at x squared minus 3 over 3x. However, well, in this case, I still can't use 0. But if there wasn't an x here, I can increase the domain by doing this. In other words, even if I can simplify it, and I can eliminate something from the denominator, like an x or x times something, I can't put 0 back into the domain. But I do know my function will just look like this, right, if I graph it or if I try and evaluate it. Okay. I think this is a better example of that. This next one. I have x squared minus 2x minus 15 over x minus 3. Well, if I factor this, what do I find? I have x, I'm going to guess, since the factors here are either 15 or 1 or 5 and 3, well, 5 and 3 differ by 2, so those are probably going to be the factors. When I say 2, I meant 5 and 3, yeah. And one of these has to be minus and one has to be plus. Does anyone want to tell me which one the minus? You see how, in other words, we're going to do FOIL here, looking at the inner and the outer to see what's going to give us minus 2x. See how we do that?
Minus 5 and plus 3.
Okay, does everyone see that? How we did that? Thank you. Okay, over yeah, you know, it's just what I'm doing today. I'm making silly mistakes. I wrote this down wrong. I wanted to write plus, sorry. And that just switches these. All right, sorry. Okay, so in this example, you see x minus 3 over x minus 3, except at 3, this is 1. So I can simplify this to x plus 5, which is very simple, right? That's just a straight line, except I have to remember x cannot be 3. And if I asked you what the range was, well, you know, a straight line is going to have all real numbers. But since I can't plug in 3, what would I get when I plug in 3? I'd get 8. So, you know, somewhere along here, I guess at 3, it would be 3, 8. And I would have to kind of eliminate that point from the range. It can't ever be 8. All right. There's another version of this you need to kind of be aware of. It's just a simple difference, but you might not notice it right away. Now this is a more complicated example, but 2x squared minus 9x plus 4 over 12 plus x minus x squared. Okay. Well, I didn't write this down in a very nice way, did I? But we're just gonna go to the factoring and then we'll verify it. So this should be 2x minus 1 over x minus 4. And this should be 3 plus x times 4 minus x. Let's check that. So the firsts are 2x times x, that's 2x squared. The lasts are minus 1 times minus 4, that's plus 4. And the inner and outer are minus x, and 2x times minus 4 is minus 8, so minus 9x. So that factoring is correct. Now here, well, 3 times 4, that's the first, is 12. X times minus x is minus x squared. Okay, that's good. Then we have the inner and the outer, 4x minus 3x is just x. Okay, so that's the correct factorization. It might not be obvious, but here we have two factors that are very similar. X minus 4 and 4 minus x. And if I want, I can rewrite this as rewrite this up here. I rewrote 4 minus x as x minus 4 times minus 1. Because if I were to distribute this minus 1, I'd get minus x plus 4, or 4 minus x. I just want you to see that even though these, look different when they divide out, instead of 1, you get minus 1. We still have that problem that, x cannot be 4, and x cannot be minus 3 here. Okay. Sorry, I have to stop for a minute and catch my breath. All right. Okay, so these are rational expressions. We need to know how to simplify them. Need to know that when the denominator is 0, the domain has to be excluded from that point. just like fractions, we can multiply and divide these. So let's take a look how that works. If you know fractions real well, you think of these as fractions, then this will come natural. It's just a little more work, a little more complexity. All right, let's look at an example. Let's say I have two rational expressions, x squared minus 4 over x plus 3. I want to multiply it by 2x plus 6 over x plus 4. Well, regardless of what simplification I can do here, the domain still will exclude negative 3 and negative 4. Again, we have to be careful we don't divide by 0. As with numbers, one way, excuse me, one thing we might try is we might try factoring these before we multiply them. So x squared minus 4, someone want to tell me what the factors are? And this is that pattern you should try and recognize. Yes?
So x plus 2, x minus 2.
X plus 2 times x minus 2, thank you. This is over x plus 3. And now here, we're just going to factor the 2. All right, just like with fractions, you see x plus 3, x plus 3, x plus 4. Oh, wait a minute. Did I do that right? Did I write this problem down wrong again? Ah. It's supposed to be x plus 2, sorry. I know everybody's had one of these days, but it's just been that way. I'm sorry. I shouldn't complain. It's not pouring. The sun may come out someday. It's nice weather. We all have jobs. I have the teacher, you're the students. All right. Okay. Where was I? Okay, so this should have been x plus 2. I can simplify that. And I'm just left with 2 times x minus 2, or if you like, 2x minus 4. Keeping in mind that my domain is still doesn't have negative 3 and negative 4. This is my result. The range of this, because it's a line, will be almost all real numbers, except if I plug in minus 3, I get minus 6 minus 4 is minus 10. Plug in minus 4, get minus 8 minus 4, minus 12. So the range will not include these, all real numbers except minus 10 and minus 12. All right. Went over my board space here. All right. Just like fractions, if I want to divide, I could also write this again, writing carefully x over x plus 3, or over x minus 1. Just like with fractional numbers, instead of multiplying, instead of dividing, I'm going to multiply by the, I know it's been 10 minutes since I used that big word which began with an R. Thank you. Okay, what's the reciprocal of 4 over x minus 1? Oh, I saw that scratch. You can't, no?
Is it x minus 1 over
X minus 1 over 4. Okay. All right, so that's how I'm going to do my division with rational expressions. You know, you can, this is x squared minus x if you want to multiply it, and 4x plus 12. All right. We've covered almost everything. We haven't covered adding and subtracting rational expressions. Let's take an example. Start with a simple example. If I had 7 over 6x plus 5 over 8x. Well, I could use that, that formula, AD plus CV over CD. But that would involve multiplying multiplying these two together and ending up with an x squared, which we don't really need. They both have this factor of x. So it might be, in this case, better to factor out the 1 over x. Okay, now we can use that formula on these numbers, right? It's 56 plus 30 over 48. 1 over x, and we can simplify that. We're not gonna go through that. But we might not be so fortunate. We might have a problem more like this. (6x) over x squared minus 4 plus 3 over 2 minus x. Well, again, we could use that formula and just multiply, but it behooves us to factor first. So here we have 6x over x minus 2 over x plus 2. And here we have, I'm going to do some, fast hand waving here. I'm going to make this minus 3 over x minus 2. Now, does everyone see how I did that? I multiply the top and the bottom by minus 1. So I get minus 3 on the top. Instead of 2 minus x, I get x minus 2 on the bottom, because I want to have the same factors on the bottom. So now I have to multiply this by what? So that I can add them. What do I have to multiply it by to get a common denominator? Let me see if I can present this in a different way. If I had 5 over 7 times 2 plus 3 over 7, and I want to add these, I want them to have a common denominator. What am I going to multiply this by?
2.
Over 2, right? Which is 1. It's the same idea here. What's missing? What do I have in this denominator that I don't have in this denominator?
X plus 2.
x plus 2, x plus 2, right? Okay, well, how does that turn out? X minus 2 times x plus 2, that's our pattern. So that's x squared minus 4. Now we have minus 3x minus 6. And we're done. Okay, why don't we try a few examples? Try this one. I should multiply these together and simplify as best you can. Someone want to help you with this? Yes.
So what I did, what I did first was, I like simplified the denominator, so it's x minus 3, yeah, x plus 3, so I can like see it better.
Mm-hmm.
Then you do, yeah, times x minus 3, so I wrote that, x plus 2. Then I saw that you can cross out x minus 3, x minus 3. So I crossed out.
Slow down a second, let everybody take a look. Everybody see how we did that? Go ahead.
Okay, so then that leaves you with x plus 1 at the top, then over x minus 3 times x.
No, we got rid of that.
Oh, yeah. So x plus 3 times x plus 2.
Okay, now you could FOIL this.
Yeah.
Not FOIL it, it just depends on what you want to do. Note, in the final expression, we know that x cannot be equal to minus 1, because that would be 0. X cannot be minus 2. But we can't forget that we got rid of this. It still can't be, oh, these are knots, cannot be 3. Is everybody good with that? That's kind of, all right, let's Let's try something. Let's try one more. Let's try, say, 3 over x plus 1 plus 2x over x plus 2. Just give that a shot. All right. I want to note this is a perfect example where you can just apply this formula here. Someone want to help me out? What do I have in the denominator here? Oh, my ink goes bad. Anyone? Oh, you answer all the time.
Your
Go ahead.
denominator is x plus 1, x plus 2.
Okay, that's my BD, my
Yeah.
2 denominators. I didn't have any way to simplify, right? They're 2 different factors. Just like
Yeah.
5 and 7 or 11 and 3, no common factors. Okay, does anybody else want to tell me, what do I get up here? A times D, right? So it's 3 times x plus 2. And then here, my BC, that's 2x times x plus 1. And then, I might want to rewrite this. I get 3x, 6, 2x squared, 2x. I might want to simplify it out, but that's a different issue. Oh, what I do want to do, I do actually want to do that just to check. 3x plus 6 plus 2x squared plus 1. So that's 2x squared plus 3x plus 7. Well, I might want to check to see if I factor this, whether this is one of the factors. Now, since I have a 7 here, it ain't going to happen. But it could. We could, just like if you're adding fractions. Yes?
When you add the x's, isn't it plus 5x? Because 3x plus 2x equals 5x.
No, this is 3x. Oh, I'm sorry. You're absolutely right. This is 5x.
Yeah.
And, plus 6. Okay, so you might want to check. That could have a factor of, it could be x plus 2. We might want to see if this has a factor of x plus 2. We can simplify here. But that will have to wait for a later date. Okay, I will try and get the assignment out tonight. If not tonight, certainly by Friday. And you can have till Thursday to do this assignment. We have on the 9th another midterm coming up. Before we get there, I will provide you, know this, things we've gone over sheet, and I will give you, at some point I'll tell you specifically, we're gonna cut off, I'm not gonna make you do problems on the exam that we learned about the day before. So,